All right. Hello, everyone. Welcome to another episode of Robo Papers. Super glad to have Nadun and Zhenyang, two of the co-authors from this paper called SAIL, Faster Than Demonstration Execution of Imitation Learning Policies. I first saw their oral session and choral. I thought the result was super impressive. So really looking forward to this sharing. Thank you so much for making the time, guys. Maybe as a start, both of you can share a little bit about yourself first before we dive in.
Yeah, absolutely. Thanks so much for that generous introduction, Michael. So my name's Nadun Arachchige. I am a second-year PhD student at Georgia Tech working with Professor Danfei Zhu, and my research mostly focuses on robot learning systems, specifically how you can make those systems more robust, efficient, and applicable for industry.
Yeah, hi everyone. My name is Zhenyang. So I'm from the same lab as Nadun. So I'm also a second year PhD at Georgia Tech. So my research interest is mostly on the robot learning, especially on the system side, and also pushing the limit of how robot learning can do on real robot, and also like synthetic data for robot learning stuff. Yeah, very happy to be here today.
Yeah, and super excited
Alright.
to be sharing SAIL with y'all.
Cool. Yeah, I know you guys have a presentation. Maybe you can
Yeah.
just share that and then we can start.
Yeah, we're excited to hear about it.
Go ahead and get started here.
Okay.
Real quick, we'd like to thank all of our co-authors. It's a pretty big list, so we're not going to sit there and actually read everyone's names out, but we appreciate all of them, and this wouldn't have been possible without their help. So starting off with a little bit of motivation, right? So we've seen, particularly with robot learning and these newer models and architectures, they're able to do a lot of different tasks, and they're able to generalize really well, right? But if you actually look closely at some of these cool demos, I'm gonna poke fun at one of my I guess colleagues here at Georgia Tech, Simmer Career, who actually led this project, Mimic, and he's totally fine with this. But if you look closely at a lot of these demos, right, you see that they're sped up. And in this case, sped up even 8 times. So even though these capabilities are incredible in terms of generalization, accuracy, there's still a lot lacking when you compare robot learning systems to industrial robots, right? And industrial robots have been able to achieve really fast throughputs and really high repetition rates for decades even, right? And so if you actually want to transition these robot learning systems from the lab to actual industry and to try and find effective uses for them, we kind of have to tackle this issue as well. We kind of have to look at, okay, how do we bridge the gap between classical robots, their speed, and robot learning systems and robot learning robots that have better generalization and work better in uncontrolled environments, work better in clutter with objects that are diverse, different textures, shapes, that kind of thing. And so this is what SAIL attempts to do, right? We try to answer the question, can we actually execute these visual motor policies faster than demonstration? And so SAIL stands for Speed Adaptation for Imitation Learning. So to start off with, I guess, a little bit of background, for our viewers, when we train these policies, what we'll typically have is a demonstrator, right? A human that actually goes in and teleoperates the robot. And then at the same time, we're collecting all of this data. We're collecting what the robot sees through cameras mounted on the robot or externally. And we're collecting those actions that the human generates during teleoperation, right? Where did they actually move? Did they open or close the gripper? That kind of thing. And so when you train a policy on that, at best, it will typically match the same speed as the human teleoperator, right? And we're typically not great at teleoperating robots fast, because it's a different embodiment. We want to be safe. We don't want to break the robot, right? And so when you deploy these policies, they're going to be executed at the same speed as the human teleoperation, which is a big limitation. But as a little bit of a teaser, with SAIL, what we're able to do is actually speed up that execution, right? Much faster than what the human demonstrator could do. And, owing to that, you can actually get policies that are more reactive and also recover quicker from failures, as you can see here on the right. Right, so you're able to get higher throughput and more efficient, more efficient execution. Right. So when you think about it, why exactly is this difficult? Right. I mentioned the fact that demonstration data that the policies are trained on is slow, right? But this necessarily isn't a limitation for the robot, right? You can take those trajectories, right? You can take those initial trajectories and you can just speed them up even arbitrarily, right? But what actually happens when you do that, right? Well, why isn't this an easy problem? To answer this, we kind of have to look at the whole system, the whole robot learning system, as well as the different components that interact within the system, right? So for a visual motor policy, what you have is you'll typically have your sensors, right? Your cameras or perhaps even tactile sensors that generate that sensing data that goes into your neural network, right? So you have your observations or the state environment that goes into your neural network, and the neural network looks at that and generates a trajectory of actions, right? And typically this trajectory will be for a short horizon, right? It's not going to, for most cases, it doesn't complete the whole task, right? You're going to be completing parts of the task, perhaps a second or, even longer than that. And when you send this reference trajectory to your robot controller, what it does is it will generate, some low-level control commands like torques or joint velocities that then get converted into torques. And those are the actual control commands that the robot receives and executes, right? And so the robot then acts in the environment, and this is back and forth interaction between the environment and the robot. And then as the environment changes, you get new observations, and those pass in to your neural network again, which again generates reference trajectories, and you have this cycle that keeps continuing, right? And the interesting thing is, or really the thing to note here is that each one of these components interact with each other, right? And so when you change, say, just the robot controller, that's going to change how the robot interacts with the environment. It's going to cause dynamic shifts in the environment, which in turn will change what the neural network sees. And as the neural network sees something different, perhaps it's something it's never seen before, it's going to generate different reference trajectories, right? So we have to keep in mind, we have to keep this in mind, right? And we have to design our system around this and try to minimize the differences between our initial data collection and the actual execution that happens when you speed up your policy execution, right? And so the first thing that we have to account for is latency, right? Or the latency of the whole system. So if you were to just take your trajectory of actions that the policy generates, a half second or a second of actions, and if you just run through this really fast, this is what happens, right? You get really jerky motions. And the reason and the reason why this happens is you have this, trajectory of actions that the policy generates, and then you send those to your controller, and then you tell your controller, okay, go through these actions really fast. And it can, in most cases, it can do that. So your robot starts moving really fast, but then it runs out of actions, right? And it pauses. It waits for more actions to be generated from the policy. And as that happens, your robot has to find a way to take all of that momentum, right, all of that inertia, and stop really quickly. As an analogy, it's like if you were trying to run a 100-meter sprint, but every second you decide to stop and think about what you're going to do, right?
That can't possibly be good for the robot, that sound that it's making.
Yeah, absolutely. Right. It is very painful, as painful for you to do that, but it's also painful for the robot.
So Nadun, can I ask, like, the source of this latency that you just described? Is it the inference latency? Is it just the robot execute the actions faster than your model is able to give control instructions?
Yeah, that's definitely the major source of latency in the system, right? But then you also have all the other things on top, like your sensing delays, but also your pre-processing or even post-processing of the actions, right? And all these delays add up. But definitely the inference delay is a significant portion of this delay, all right? And you can see the robot just pauses, waiting for the inference to complete, right? And this is what most prior robot learning systems do, and it's kind of like it's kind of a an issue that folks have ignored for the most part, right? And if you think about it, it in itself causes this dynamics shift or distribution shift between your data collection and your actual deployment. Because during data collection, as humans teleoperate, they're not pausing every second or half second, right, to generate more actions. So we typically teleop in a continuous way. And so when your policy is actually being deployed, this changes the dynamics, right? Even if you're to do it at a slower speed. For the most part, this hasn't been an issue because we typically do, quasi-static tasks. So we can get around that. But if you're to try and do really dynamic tasks, or if you're trying to speed up, it definitely becomes more of an issue, right?
So can I ask a question, a follow-up on that then?
Yeah.
So the problem here is that you have an action chunk, which is maybe half a second long, and it's trying to execute this. But then because you've compressed that, now there's still inference happening, and so it has to stop. Why not use a longer action chunk?
Yeah, great question. So it's going to be...
It's okay if you'll get to it later or something. Also, we can just say, oh, look.
No, I mean, it's definitely a great question, and folks have tried to do this before, right? But it's going to be a trade-off, right? With longer action chunks, as you go down the line, your later actions are typically going to be less accurate because these policies are not the greatest at modeling longer horizon actions. And the other thing you have to keep in mind is it makes your whole system less reactive to changes in the environment, right? So if you can imagine, a task where you're trying to track a ball that's rolling around, right? If you're to take a longer action horizon, maybe plan out 2 seconds in advance, right? Then you're not going to be able to quickly adapt your motions, or the policy is not going to be able to quickly generate motions that adapt to changes in the motion of the ball or whatever object that you're trying to track, right? So there is this, trade-off between how often you run your inference and how long of an action horizon that you use. So yeah, and sorry, did you have another question?
Go ahead.
Right.
That makes
All right,
sense.
cool.
Just saying. Yeah.
So yeah, and other folks, like the incredible folks at Physical Intelligence, have noticed this issue as well. So this is most of y'all probably familiar with this work, real-time chunking, where they're trying to do the same thing, right? They're trying to get over this issue of having a wait for planning, and with this, they're able to do these like really cool tasks and create these really cool demos as well. And so when you look at it, going back to Michael's question about like where these different latencies come from, part of it is going to be your observation delay, right? There's a frame rate that your cameras can run at, and then there's also going to be your inference delay. So how quickly your policy can take in those observations and generate an action trajectory for you. And so while that is happening, your robot is waiting for those new actions. And this is what happens during what we call sequential or synchronous execution, right? And this results in the jerky motion that we're seeing. So one way to try and deal with this is through asynchronous execution. So while you're executing your previous chunk of actions from the policy, you run inference again. So you kind of have this, receding horizon control where your horizon keeps moving away from you, right? So you never really perhaps run out of actions if you do this in a correct way or do it in a smart way. But it comes with its own challenges as well. So by doing receding horizon, the first thing is you got to make sure that you run your inference frequently enough that you never run out of these actions, right? But this becomes challenging when you start speeding up, right? Because look at your execution horizon. Decreases as you speed up. So you have to keep that in mind, and you're always going to have this upper bound on how fast you can speed up due to your fixed inference rate and observation delays, right? And so you're going to have this gap when you do speed up, even if you were to run asynchronous execution. So naturally, that's going to cause distribution shift. And when you think about asynchronous inference and execution, it comes with its own set of challenges. And one major challenge is the the divergence of predictions from your policy, right? And the reason why this happens is when you look at the best performing policies that we currently use, right? They typically encode some level of multimodality in the actions that they generate. And this is a desired behavior, right? Because there are multiple different ways to do a task. So you don't want your policy to collapse to just one of those modes, right? You want it to be able to generate multimodal behaviors and model multimodal behaviors, right? Perhaps coming from, demonstrations may come from different demonstrators, perhaps, but even the same person demonstrating the same task can have between demos may choose to do it different ways, right? So you want your model to be able to model that. So here we have an initial trajectory that's generated by your policy, right? And for asynchronous execution, what we're going to do is we're going to execute part of that, right? And the robot is able to track that trajectory depending on how good your controller is with, high enough fidelity. And then at the next time step, before you actually run out of these actions, or before you run out of these, run out of these future actions, as you can see in the blue dot, right? You're going to start your inference again. Naturally, this is going to have an inference delay, so you're going to keep executing actions from your prior trajectory. But then the problem is your new trajectory may not agree with the prior one, right? And so you can see this new trajectory here in green, it decides to diverge from the prior trajectory at the time of inference, right? So what this might look like is you may have, say, an obstacle here in the middle between the two trajectories. And what your policy decided to do first was go above it, but for its second prediction, it decided to go underneath it, right? And so when this happens, you quickly have to switch over to this new trajectory because you're going to run out of actions from your old trajectory, which again is going to be really painful for your robot. Now you have this huge gap between where your robot is and where the next set of actions are going to take it. Right? And what does that look like on a real robot? You can see it sort of oscillate. Right? And this and that oscillation is due to this like vicious feedback loop where the policy sees that it's maybe further away from the object that it's trying to interact with, and it decides to go one way, but that prediction is perhaps too far of a correction in one direction. So the next time step, or for the next prediction that's happening asynchronously, it tries to come back, right? And this keeps reinforcing during the control loop. You can see the robot try to oscillate between these different modes. So once again, these divergent predictions, I'm just going to run through some of these problems at the start, and we'll talk about like how we try to address some of these later on. But this divergence in the predictions is going to cause distribution shift once again, because the policy hasn't seen this in its training data. And finally, or not finally, but another significant source of this distribution shift is the change in the controller dynamics when you actually speed up your execution, right? So going back to our demonstration data, what you will typically have is a set of poses that you command the robot to go to, perhaps by using, like a joystick, or in this case, a VR controller. And what the robot is trying to do is track the relative changes in the motion of the VR controller. The robot is never really going to reach those poses exactly, right? Because when you think about the controller, it needs kind of an error to generate those torques, right? So you're going to actually have a set of poses that the robot ends up reaching, which are always going to lag behind the set of poses that you command it to go to, right? And it is this error that actually generates the torques. And so when you execute your policy at the regular speed, this typically isn't an issue, because you're going to still have that same motion profile in blue that your robot ends up reaching, because your controller is the same as it was during data collection. But when you try to speed up your policy execution, here's what may end up happening. Your robot may undershoot or overshoot and ends up going to poses that it didn't go to during the data collection, right? And so your motion profile ends up being warped and completely changed. And this is due to the change in your controller dynamics. So if you take that same controller and tell it to move quickly, it's not going to be able to track those poses that it did during the data collection as well. And once again, this leads to distribution shift, right? And it leads to these failure cases that the policy is not able to recover from. And so this is where SAIL comes in. And what we try to do is, we take each of these components and we try to minimize the ways in which they cause distribution shift, or also try to minimize the failure cases or the impacts that they have on our robot learning system when you start speeding it up, right? And this is at two different levels. We're going to have our policy level first, which tries to deal with the multimodality that we saw earlier, right? Those divergent predictions. And the way we do this is through a method that we call error adaptive guidance, right? We're guiding the policy on its previously generated trajectory so it can generate a new trajectory that is congruent with the previous one, right? That agrees with the previous one, right? And so now you no longer have that issue where the robot has to jump to a new trajectory or a new reference that is, further away from where it is. And so,
Nadun, sorry, I have a quick question. So this one is, can you clarify? Is this error adaptive guidance? Is it just something you do directly at inference, nothing to do with your training, or is it actually part of your training pipeline?
Yeah, so there are different ways that folks have tried to, guide policies, especially for asynchronous inference, right? So if you look at, the work by Kevin Black, real-time chunking, what that is a totally like an inference time trick, right? Where you take your prior actions and then in-paint them during your denoising steps. During your action generation. What we do is what's called classifier-free guidance, right? So this does require your policy to be trained slightly differently. So during train time, what we actually do is we pass in as observations to the policy the future actions, right? And what this allows the policy to do is look at those future actions, and it kind of cheats. It just looks at those future actions and says, okay, I'm just going to generate these again, right? And so, yes, we do have to make slight changes at training time, but it isn't like a massive change to the policy architecture. All it is really is an additional observation that's passed in. And so why we call this error adaptive is during the policy execution and during the actual robot deployment, we decide when we want to pass in this conditioning, right? And when does the conditioning make sense, right? And so once again, all it is the policy takes in a set of actions, and then it generates those same actions at the start of its next prediction, right? And so at that at that switching point where you go from your old reference trajectory to your new reference trajectory, at least the first few actions of your new reference trajectory are going to be somewhat in the same region as your old trajectory.
Got it.
So yeah.
So this is kind of like resolving switch, what do you call that? Like chunking inconsistency between your current chunk and the next chunk.
Absolutely.
Basically forcing your next chunk to be the first few micro steps of your next chunk to be what has been executed the previous chunk, the last few steps. Okay,
yes.
Got it. Okay. And you do that actually at the training stage, so that it learns this behavior at training.
Yes.
Got it. Okay, cool.
Why is this necessary? I'm sorry. Why is this necessary? Like, why can't you just splice together the previous action into your trajectory or something like that? So is the answer that the underlying like flow matching policy is actually learning to make a smooth correction or something like that? Like, why is it? I'm trying to understand why this is important, I guess. Still.
Yeah, absolutely. So part of it is that like you're gonna have more of a smooth transition between your two reference trajectories. But if you were to go back and see, what happens when you don't do this guidance, it is actually quite difficult to try and splice these actions together, right? So you could maybe do some sort of spline interpolation from this action all the way down here, but then it might, end up taking your robot into new states that's not supposed to go in. So if you would imagine there's maybe an obstacle over here, if you were to try to quickly go from here down here, it may end up impacting that obstacle, right? So trying to do this, more simple splicing may not end up working.
So in this diagram here, which parts of this are I guess from the error adaptive are the actions that you would provide as conditioning? Are they the parts before green?
Yes.
Basically.
So
yes.
So these actions right here get executed during the inference delay, right? Because the policy is still thinking. So these would be the actions that actually some actions into the
future. So you pass in
well.
all the actions that are happening during the inference delay, so that it knows where. Okay, yeah, makes sense.
Yeah.
Okay, cool. I follow.
I have another follow-up question. Like, how do you know? Like how do you determine how how much of that next chunk, like the first few steps, like how many micro steps, is it an arbitrarily fixed thing, or is it also depending on something like a dynamic parameters? Like for example, very naively now in your left diagram, you have this 4 yellow line, right? So presumably you decided, okay, the initial just means 4, but how do you pick this number 4?
Right. So how many of your next action chunk that you want to
Do
actually
this EAG.
condition on or apply this conditioning to? Was that
exactly?
your...
How yeah, exactly. How do you determine what is that? Like yeah, is it specific to the system, or is it's yeah?
So yeah, part of it is going to come from like practicality as well, right? So when you, for example, when you start speeding up your policy, how many actions do you actually have left to condition on, right? So if you're running out of actions in your initial trajectory, then you're not going to have too many to condition on. So part of that is also, again, a design choice, but more comes from the actual limitations of your system, right? And the other part is how reactive you want your system to be. So if you condition on too many actions, then your robot is going to commit to the previous actions, right? Or the previous decisions that the policy made. So if there are changes in the environment, then it can't quite react to those changes as quick, right? So it's going to be this kind of, once again, it's going to be a balance between how many actions you want to condition on to smooth out that transition, but also how reactive you want your system to be. And typically we find that a few actions, like if you're thinking about like sped up execution where you're running through your actions at 100 hertz, right? Just around the order of about 6 to 8 actions of conditioning. So that's less than 100 milliseconds, right? But if you condition on about 6 to 8 actions, that's typically a good amount to be able to still maintain smooth motion.
Is that the amount of actions that take you to the end of the previous inference? Sorry, of execution of the previous inference action chunk? Like, is that the hard minimum, or can you go below that?
Yeah, you can definitely go below that. So
okay,
depending on how fast you're able to run your inference,
sure, okay,
how long the previous action chunk is, you don't have to condition on all of them.
Interesting. Yeah, I suppose this is the kind of detail that the only when you start to actually apply this in the real system, then you figure, oh, okay, it's turns out it's around 6 to 8, and let's say 100 hertz. Okay, that's very cool, very interesting. Right, thank you.
So now you're going to have much smoother motions when they actually get executed, right? But sometimes, here we go. Yeah, sometimes we actually decide to not apply this guidance. And so this is when, you may want your robot to be more reactive, right? So if there's maybe a large tracking error, then you don't want to have the robot commit to its previous generated actions, right? Or the policy's previously generated actions. You want it to be able to react much faster to changes in the environment. So we'll decide when we want to apply this guidance, mostly based on the tracking error of the robot. So on the left here, you can see what happens when you don't apply that guidance. The motion is considerably less smooth, as you can see in the plots, but also it takes the robot, as it's going between these action chunks, it takes a while for it to catch up to its previous actions, right? And this in turn reduces how fast it can actually do these tasks. So the next thing is when you start speeding up your policy's execution, there might be certain stages in your task or certain stages in your motion that you don't want to speed up, right? So here on the left, we have an example. You can see when it goes to grasp that banana, it misses its grasp, right? And the reason why this happens is because the gripper moves much slower than the actual robot arm itself. So in these cases where it's maybe interacting with an object and you want it to have like a really firm grasp, or it's doing some sort of motion that requires it to slow down, you want the policy to be able to autonomously decide when to do this, right? And the whole system to autonomously decide when to do this, when to slow down. And so our solution was to use motion complexity analysis to determine when to slow down. And so one of the methods we built on is called automatic waypoint extraction by Lucy Shi and Archie Sharma. And what this method does is it tries to approximate your initial demonstration trajectory by a few like waypoints, right? And what you can notice is when you look at these waypoints, if you would have just, free space, straight line motion, you're going to have fewer waypoints in those segments, right? But if you would have more complex motion where the robot is interacting with objects, those are going to naturally have more waypoints to try to approximate that motion better. And so what we can do is once this waypoint generation is complete, we can apply a clustering algorithm on top and try to cluster these waypoints into segments of complex motion and segments of free space motion where you can freely speed up your motion, right? And so once you have these segments, you can take your original demonstration trajectory and label each one of those actions as being in a complex motion region or a free space motion region, right? And this could be, depending on how complex you want to make your system, this could be a continuous value that determines how fast each action is supposed to be executed, or it could just be binary if you want to, make your life easier, right? So you have 1 for complex motion and 0 for free space motion. And this can be easily, once you generate these labels, you can easily train your policy to generate these labels during execution, which is what we did.
And are the labels done at each action chunk, or is it in fact done at each micro steps?
It is at the level of each action.
I see.
Each action. And during execution, there's a few design choices with what you want to do with that, right? During execution, if say you're planning out a second in advance and any of the actions, right? You may have for a second in advance, you may have 20 actions. If any of those actions say slow down, you may decide to slow down your whole chunk. Or you may want to do some sort of voting where you take 50% of the actions. If they say slow down, then you slow down. Or you could have a mix. So you can decide which action you want to slow down for in your action chunk, and the rest of them you execute at the fast speed. So yeah, once you apply that adaptive speed modulation, this is where you can see. So you can actually see the robot slow down as it goes to grasp the object. And for the rest of the motions, which are free space, it speeds them up. All right. So now that we have that, we also have a action scheduling module, and this is on the system level, right? So if we think back to some of those issues that we had with your inference delay and your actions running out, what you want to do is make sure that when you execute your reference trajectories and when you execute the actions, you have enough actions where you're never going to run out ideally, right? So your robot never has to pause, but also you run your inference at a high enough rate that you can always keep extending out that horizon, right? So you can keep generating more and more actions, and your robot is happy and you're happy. And another thing that we want to do is make sure that we match that same motion profile as during data collection. So for that, what we did is we take our initial, robot controller, but we tune those gains up really high, right? So on the bottom right here, we saw the issue with the motion profile. You have a different motion profile and your robot ends up in states that it's not supposed to. On the left, you can kind of see what that looks like, right? So what we end up doing is we take those, actions that the policy gives us, but we tune up the gains of our controller, and we train the policy on the actual reached poses and not just the commanded poses. Because if you were to take a high gain controller and execute those commanded poses, you're going to end up with overshoot, right? And the policy and the robot is still going to end up in locations that it didn't during the actual demonstration. And we also have feed forward control where the controller looks at future actions, right? And tries to optimize the generated torques to be able to better track not just the current reference point, but future reference points as well, right? And once you combine all these different design choices and all these different components, what we're able to see is compared with a baseline, we're able to get almost 3 times improvement in throughput, which is the successful or successes in a given unit of time. And so real quick, some demos. This is a cup stacking task that we wanted to do just to highlight both the high precision aspect, but also the speed up of our policy.
Nadun, I'm curious, besides the speed up, do you think the fact that it is more responsive, as a system in total, it actually also overall improve success rate?
Absolutely, yes. And this is something that other folks have also noticed is, for certain dynamic tasks, if you were to just do the thing where you predict, execute, right? It's not going to have the same outcome as if you were to continuously take actions. So yeah, that's totally the case. By being able to react to changes in the environment faster and being able to make these decisions faster, our policy is actually able to, and the system is actually able to complete some of these tasks better and end up with higher success rates.
I'm curious also, so you mentioned, I think, maybe 3 very core ideas that you guys apply, right? 2 at the policy level and then 1 at the system level, the high gain post tracking. What would you say out of these 3, like, is the one that moved the needle the most? Like, let's say if you were to drop 2, or you can only keep 1, which is the one that you absolutely need, you feel that you need to keep?
So here's the challenge. I don't think we could drop any of these, right? So, definitely without our adaptive slowdown, you're going to have like lower success rates. And then without our high gain controller, if you were to look at just the throughput, these are results from Sim. If you look at the throughput, it is definitely much slower than with. So yeah, I definitely want to say that all these components are going to be impactful, but also on the system side, with your real controller, that's something that perhaps robot learning researchers need to look into more. Is how can we better design these systems, and how can we better design the different components of the systems to be able to do some of these things that we want to do.
It did look like in that plot that adaptive slowdown always hurt at least one of your tasks, right? Yeah. So do you think that there's something to be improved there, or do you think it's just like the quirks of that task?
Yeah, it's definitely depending on your task, right? So if you have like a really complex task where you have maybe peg and hole insertion, right? What your policy is going to end up doing is, as it gets closer to grasping either the peg or inserting the peg, it's going to predict a lot of these slowdown actions, right? And so that can maybe impact your throughput. But also at the same time, maybe a failure costs much more to you than a success in that case, in which, in which circumstance you don't want to speed up if it could potentially result in a failure, right? If you have like a really fragile object or a really expensive, computer component that you're trying to insert, maybe, right? So yeah, it's definitely going to be this balance between your throughput, how many successes you get in a unit of time, and your success rate, which is your overall, like how many successes can you do?
Makes sense.
I guess I'm also curious, like, with something like SAIL, what is the impact on the requirement of the quality of this like teleoperation data, like that you ask a human to do? I often hear that for research teams who are trying to use teleop data to do imitation learning, it's very important to train up the human teleoperator. Like that guy needs to be very highly skilled. I wonder with something like SAIL, does it mean that you can actually accept so-called lower quality, or the requirement is still the same? What do you think?
Yeah, at least with
Or is it
our,
higher?
or is it higher? Yeah,
Yeah.
it definitely. I mean, we have done this. We have done some like experiments where we combine, SAIL with Dagger style methods. So this is like online interactive learning, during policy execution to collect more data, and it'll improve, right? So yes, the data quality definitely matters for SAIL, less so in the terms of like how fast the human can do the task, but just in, do they succeed most of the time, right? And we definitely only keep successes in our demonstration data. So yeah, we want to make sure that, our data is relatively clean. It can be noisy in terms of the demonstrator might decide, different ways to do the same task. That's relatively okay. But for the most part, they should be successes. Motion should be relatively smooth, because if the reference motion from the demonstration data is smooth, that just makes the rest of the pipeline that much smoother as well. So yeah.
Got it. Okay. What would you say are some of the limitations now or things that you would love to improve? Or I don't know, maybe you have more things to share.
Yeah. So here's one. The robots that we mostly evaluated in this project were cobots, right? So it's safe to work around, in a lab environment. But with them, you're going to have like torque limits, and a lot of times we were hitting the limits of the robots themselves, during execution as you try to speed it up, which is fair because these are meant to be safe projects, right? So some of our future work is going to focus on actually deploying this whole system, and we've started on this already, but deploying this whole system on more industrial robots, like this robot right here that can move much faster than the UR5 and the Franco robots that we were using, but also try to integrate some of that information about the torque limits of the robots into that generation. So now you can kind of ride at the limit of your robot's capabilities as opposed to going underneath, like, slower than the robot is capable of, or maybe even exceeding the robot's speed, right? And additionally, there's a bunch of different things like safety. Naturally, as the robot starts moving faster, it's going to be more dangerous. So we want to maybe apply these really robust and real-time safety controllers on top that can look at some of the actions that a policy generates and decide, is this going to take my robot into an unsafe state, or is it going to break something, and kind of bring the robot back into safer states. So those are two things we're currently looking at. So yeah, with that, I'd like to thank once again all of our co-authors and collaborators. This was definitely we're very much a team effort, and very much a significant effort on everyone's part. So, and we have
Yeah, thank you. I mean, your
Yeah.
your presentation was super well done. I thought like it's you set up the problem space very well. I do have one, I guess maybe one more question. So I think this might have come off from one of Danfei's thread previously. Something about a trade-off of, or it's kind of like a design choice of whether you take the cost at the inference step versus, or you do your with time chunking, let's say in inference, or you do more in training. Like, do you have a view on this?
I see. So do you invest more of your effort during training or during deployment, right? Was that
Do you mean compute or do you
Yep.
mean some what other stuff?
So I think you kind of have to do both, right? Because if you think about it, if you have a really robust policy, right, for inference, sorry, I'm just going to pull up our website as well, which is going to have like additional videos and demos. But if you were to think about training a really robust policy, right? Imagine a policy that can do all of the tasks you care about at 100% success rate, right? Naturally, as you speed up, and speeding up is, maybe more inference time, problem. Naturally, as you speed up, your success rate might decrease, right? So it definitely helps to start off with a really robust policy, right? And this is where you invest more time into training a policy that is more data efficient, that can generalize to, different types of objects maybe, or different colors, that kind of thing. And once you have that robust policy, you can speed it up, right? But then speeding up as well during inference time, you're going to have to do things to address some of these issues that we talked about, like controller dynamic shift, right? And these are things that you cannot train for, perhaps, right? Because maybe your prior data, you'll never have access to prior data where your robot is moving at fast speed, right? So both of these definitely go hand in hand. And as a robot learning researcher, it definitely helps to have an understanding of all the different components and understand where best to invest your efforts and where, maybe there are still challenges that are unaddressed. So, yeah.
Yeah, this is really very cool work. Like, I always thought that, like, how can you exactly what you guys managed to do in this project? How do you, because static operation, it's naturally going to be slower than if a human were to just do it with their hands, right? But what you get from teleop data is you get all the action controls, all the nice things that you get from teleop, but it's always going to be slower. So, but yeah, as it turns out, as you guys pointed out here, you can't just do a naive speed up. You kind of have to be very speed adaptive. Yeah, it's really cool. Yeah, Chris, I don't know whether you have anything else you want to ask, or Zhenyang, do you have anything you want to add?
I think Nadun did a great job covering everything. Yeah, makes all the sense to me.
Yeah, not too
Zhenyang,
much
do you
on
have
my
any?
side.
Yeah.
Okay, cool. Yeah, maybe as a final question, we always like to ask, like, are there any like papers that you guys read recently that you want to give a shout out to? Doesn't have to be about like action chunking or this kind of thing, but anything that kind of pique your interest that you want to give a shout out to?
I think one thing very relevant to our papers is that we saw lots of similar works that looking into this direction to make the policy run smoother. So Nadun already mentioned the RTC1 from Pi, and they also have a follow-up paper doing the training time guidance, which is pretty similar to what we are doing here. Like instead of doing inference time smoothing, but considering the training data and put those compute effort in the training time. And there is also another one from Songhan's lab called the they are also trying to make the data more efficient and also running faster. So I would say there are lots of works related to this line of research that is happening, and I think people are care more about right now to actually not only you have a good operation data, but you also actually want to turn those data into the real performance on your robot based on the policy. So that will require both the design on the algorithm part and also the data part. Yeah.
Very cool. Nadun, how about you?
Yeah, definitely. I mean, I think Zhenyang covered like most of them. That I was also thinking about, like, yeah, definitely the Vilash paper. Very, good work. And let's see, one other thing that I did want to talk about is recently mostly been working on simulation generation, and we feel that this is probably going to be relevant to this problem as well, because through simulation you can kind of generate the data that you may not have in your teleop data set, right? So imagine the case where you have a recreation of your real robot environment in sim, and it is photorealistic recreation, and in that you can move your objects around faster, and you can actually replay your trajectories faster. And then you collect your data in simulation. You collect your image data in simulation, image observation action data in simulation, and then you train your policy. And then take that and deploy it on a real robot. So yeah, that kind of idea has, of trying to try to figure that out and try to see how we can best leverage simulation for that.
The simulation you're thinking about is the classical simulation, right? Like not the world model stuff, right?
More classical simulations, yeah.
Are you thinking about like still human teleop in simulation, or are you actually thinking about just generating everything?
Generating the actual data. So there's a lot of great work out there, like Mimic Gen by Ajay Mandalkar, that takes reference demonstrations from humans and then adapts them. And the problem that they were trying to do there is trying to adapt to like different preset distributions of objects, right? So you have like a few demonstrations, and then you can generate thousands of them by moving objects around in simulation and then warping your trajectory. You can feasibly look at trying to do that same style of method, but for faster motions instead. So yeah, something like that.
Cool. All right. Sounds like that's your next paper. Yeah. Okay. Very cool. Yeah, guys. Anyway, thank you so much for making the time. I thought this was really, really cool work. Yeah. Looking forward to your next one. Yeah. I guess to the next one. Yeah. We'll see you.
Thank you, guys.
Absolutely. Thank y'all.
Thank you.